Bismillahirrahmanirrahim. Welcome back in lecture 9, the discrete structures. Uh, in this lecture, we will discuss about the sequence and summations. The sequence which maybe you have already discussed in as a little part in your intermediate, and summations like these notations maybe you have already discussed, and the product notations this, and the sequences about arithmetic, geometric, harmonic sequences maybe you have already discussed. Now in this lecture we will discuss about the definitions and the examples of sequence and summations. We will discuss about today's lecture, uh, sequences, alternating sequence, summation notation, product notation, properties of summation, change of the variables, factorial notations. These are the topics which will be discussed in this lecture. Sequences. First of all, sequences. A sequence is a function whose domain is either all the integers between two given integers, or all the integers greater than or equal to a given integer. We typically represent a sequence as a set of elements written in a row. In a sequence, this was denoted by am plus 1, am plus 2, up to an. Each individual element ak, read a sub k, is called a term. The k in ak is called a subscript, or the number of the term. For example, if we in this we can say that this is mth term, this is m plus 1 term, this is m plus second term, and this is nth term. If we discuss about the finding of the terms, finding terms of the sequences, we define sequences A1, A2, A3, and B2, B3, B4 by the following explicit formulas. AK is equal to K over K plus 1 for all integers K greater than or equal to 1, BI I minus 1 over I for all the integers I which are greater or equal to 2. We compute the first 5 terms of both sequences. We can compute it. If we discuss about the sequence A1, A1 mean the first term. If we put the value of K as 1, mean its first term. 1 over 1 plus 1, it's 1 by 2. A2, so it's 2 over 2 plus 1. We replace the value of K, 1, 2, 3. Here is the question is this: we have to compute the first 5 terms. So this is the second term, and if we discuss about the third term, we put k is equal to 3. So this is 3 over 3 plus 1, which is 3 by 4. And in fourth term, we put k is equal to you can say that 4 over 4 plus 1. So this is 4 by 5, and so similarly we can find the fifth term, which is 5 by 6. And the same scenario for this sequence BI, we can find the second term B2, because we have a condition for I which is greater or equal to 2. So we start from 2. So it is 2. We put the value of I as 2. This is 2 minus 1 by 2, which is equal to 1 by 2. And if we put I is equal to 3, so B3 is equal to, it is the third term, 3 minus 1 over 3. So this is 2 by 3. Similarly, we can find the 5 terms of this sequence B. If we say that we have to compute the first 6 terms of the sequence C0, C1, C2 up to so on, defined as follows. Cj is equal to minus 1 power j for all the integers j's which are greater or equal to 0. So we can say that C0, it means we have to put j is equal to 0, which is minus 1 raised to the power 0, which is equal to 1. And C1, so we put minus 1 raised to the power 1, which is equal to minus 1. And similarly, we put C2 is equal to minus 1 raised to the power 2, which is equal to 1. So in C3, we put minus 1 raised to the power 3, which is minus 1. And in C4, we have to put j is equal to 4, so minus 1 raised to the power 4. So since power is even, so we can say that minus 1 goes to 1. And in C5, you can say that C5 is equal to minus 1 raised to the power 5. Power is odd, so it's minus 1. Thus the first 6 terms are 1 minus 1, 1 minus 1, 1 minus 1. It follows the sequence oscillates endlessly between 1 and minus 1. So this sequence is like the oscillation between 1 and minus 1. You can say that, for example, we can see that about the sequence of uh, the graph of the sine, which is also between 1 and minus 1. Explicit formula. If we find an explicit formula for a sequence that has the following initial terms: 1 minus 1 by 4, 1 by 9, minus 1 by 16, 1 by 25, 1 by minus 1 by 36. We denote the journal term of the sequence by AK, and suppose the first term is A1. Then observe that the denominator of each term is a perfect square. Here you can note that 4 is the perfect square of 2, 3 is the perfect square of 9 is the perfect square of 3, similarly 16, 25, 36. So we can these terms can be written as 1 by 1 square. This is minus 1 over 2 square. This is 1 by over 3 square, and this is minus 1 by 4 square. And this one is 1 over 5 square, and this one is minus 1 over 6 square. So this is the first term. This is second, third, fourth, fifth, and sixth term. Note that the denominator of each term equals the square of the subscript of that term, and that the numerator equals to this. So we can generalize this by this formula: AK is equal to plus minus 1 by K square. If we put 1, so this is 1 by 1 square, and second we put minus 1 over 2 square, then we put 1 over 3 square. Also the numerator oscillates back and forth between 1 and minus 1. So it is 1 plus 1 when k is odd, and minus 1 when k is even. To achieve this oscillation, insert a factor of minus 1 raised to the power k plus 1 or k minus 1. or minus 1 to the raised to the power k minus 1 into the formula for ak. For when k is odd, k plus 1 is even, and thus minus 1 raised to the power k plus 1 is equal to plus 1. And when k is even, k plus 1 is odd, and thus we can see that minus 1 raised to the power k plus 1 is equal to minus 1. So consequently, an explicit formula that gives the correct first 6 terms is this: minus 1 raised to the power k plus 1 over k square for all integers. This condition is very much important. You have to write it for all integers k which are greater or equal to 1. Here we note that to making the first term in odd, would have let the alternative formula a k is equal to minus 1 raised to the power k over k plus 1 square for all the integers k greater or equal to 0. In this we discuss about the summation. If m and n are integers and m is less or equal to n, the symbol summation ak, k varies from 1 to n. Read the summation from k equals m to n of a sub k is the sum of all the terms a m, a m plus 1, a m plus 2, a n. So we say that these terms a m plus a plus a m plus 1 plus a plus a m plus 2 up to a n is the expanded form of the sum, and we write it as a k, k varies from 1 to n. This is equal to a m plus a m plus 1 plus a m plus 2 up to so on plus n. We call k the index of the summation, m the lower limit of the summation, and n the upper limit of the summation. So we can write it in the summation form as this. Here if we discuss about we compute the following summation k square. K varies from 1 to n, so you can say that you can write it as 1 square plus 2 square plus 3 square plus 4 square plus 5 square. So this is the nth term, 5 square. Now we solve all these. 1 plus 4 plus 9 plus 16 plus 25. Uh, if we let a1 is equal to minus 2 and a2 is equal to minus 1, a3 is equal to 0, a4 is equal to 1, and a5 is equal to 2. So compute the following summation series. So summation sequence is this is ak, k varies from 1 to 5, k varies from 2 to 2, and k varies from 1 to 2, a2k. If we discuss about the first one, k varies from 1 to 5. So this is the summation of first 5 terms, a1 to a5. So we can say that a1 is equal to minus 2. So we put here the value of a1, which is minus 2, and next we put the value of a2, which is minus 1, then a3 0, then we put the value of a4, which is 1, and then we put the value of a5, which is 2. If we solve these, this will give us 0. Now we find a k2 to 2, so it's the second term, which is minus 1. And if we find a2k, it means a21 plus a22. So a21 means a2 and a22 means a4. So second term is minus 1 and the fourth term is 1. So this will become 0. Here we write the following summation in expanded form. So this is also another example. Summation I from 0 to n minus 1 raised to the power I over I plus 1. So we can write it the summation into extended form. So we have to put the value of I from 0 to n. If we put here I is equal to 0, so this will become minus 1 raised to the power 0 over 0 plus 1. And in the second term, minus 1 raised to the power 1 over 1 plus 1. And in the third term, we put minus 1 raised to the power 2 over 2 plus 1. Similarly, we put 3 and go on. At the end, we put minus 1 raised to the power n over n plus 1. So this will become 1 by 1, and this gives minus 1 by 2, and this gives 1 by 3, and the last term which is not so much simplified, so this will give us minus 1 raised to the power n over n plus 1. And the final answer of this summation is 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus minus 1 power n over n plus 1. Expanded form to summation notation. Now we can write the expanded form into the summation notation. Mean to say we can put the reverse process now. Express this as the following using summation notation: 1 over n plus 2 over n plus 1 plus 3 over n plus 2. The general term of this summation can be expressed as k plus 1 or n plus k for integers k from 0 to n. So the summation of this can be written as summation k varies from 0 to n, k plus 1 over n plus k. And the second example is, what is the value of the expression 1 over 1 dot 2, 1 over 2 dot 3 plus 1 over 3 4 plus up to so on 1 over n into n plus 1, when n is equal to 1, n is equal to 2, and n is equal to 3. So what will be the value of this expression? When n is equal to 1, the expression equals to, so this is the value of 1 over 1 into 2, which is 1 by 2. When n is equal to 2, so these two terms, and so the sum of these two terms is 2 by 3. And when we put n is equal to 3, so it is 1 over, so it's the sum of three terms, these three terms, 1 over 1 into 2 plus 1 over 2 3 plus 1 over 3 4. When we add these three terms, so this will become 3 by 4. A more mathematically precise definition of summation, called a recursive definition, is the following. If m is any integer, then hence you can say summation ak, k varies from m to m, so this is am, and k varies from m to n, ak, it is equal to the summation ak plus an, k is equal to m to n minus 1 for all integers when n greater than m. When solving the problems, it is often useful to rewrite a summation using the recursive form of the definition, either by separating off the final term of a summation or by adding a final term to a summation. Here is the example said we rewrite this summation by separating of the final term. 1 over I square, I varies from 1 to n plus 1. So this is the part A. So we can write this as 1 over I square, I varies from 1 to n plus 1 over n plus 1 square. You can write the value of this. So and if we discuss about this as a single summation, so this can be written as 2 power k plus 2 power n plus 1. So this can be written as summation k varies from 0 to n plus 1 2 raised to the power k. So in certain sums, each term is a difference of two quantities. When you write such sums in expanded form, you sometimes see that the terms cancel except the first and the last. So the successive cancellation of terms collapse the sum like a telescope. A telescoping sum, some sums can be transferred into telescoping sum, which then can be rewritten as a simple expression. For instance, observe that 1 over k minus 1 over k plus 1 is equal to, you can write, we take the LCM, k into k plus 1, so this is 1 over k into k plus 1. If we use this identity to find a simple expression for this summation 1 over k into k plus 1, k varies from 1 to n. So this will become, this summation, it can be written as 1 over k minus 1 over k plus 1. When we expand these sums, 1 by 1 minus 1 by 2, when we put k is equal to 1, and when plus 1 by 2 minus 1 by 3, when we put k is equal to 2, so this will become 1 by 3. And at the end, we can say that all the terms are cancelled by each other. This minus 1 by 2 is cancelled this by this one plus 1 by 2. This minus 1 by 3 is cancelled with this plus 1 by 3 minus 1 by 4. So similarly, at the end, only these terms, last term and first term, remains. These are the remaining terms. So 1 plus, so 1 minus 1, 1 over, and 1 minus 1 plus 1 over n plus 1. These terms are remaining terms. Product notation. If m and n are integers and m is less or equal to n, the symbol product k varies from 1 to n, m varies from m to n, ak. Read the product from k equals m to n of a sub k is the product of all the terms am, am plus 1, am plus 2, an. So we write this product as ak, k varies from m to n, am, am plus 1, am plus 2, an. So a recursive definition for the product notation is the following. If m is any integer, then the product k varies from m to n, ak is equal to am, and this one, the product k varies from m to n, ak is equal to the product ak, k varies from m to n minus 1 dot an for all integers m less or equal to n. Here is the examples. Compute the following product of k varies from 1 to 5. So we put here the value of k 1, 2, 3 and 4, and we find the product of these 5 terms, so this will be 120. And similarly in the second part you can find the product of k over k plus 1, where k varies from 1 to 1, so this will become 1 over 1 plus 1, so this will give the answer 1 by 2. So here is the properties of summations. If am plus 1, am plus 2 and bm plus 1, bm plus 2, these are the sequences of real numbers, and c is any real number, then the following equations hold for any integer n greater or equal to m. ak summation ak, k varies from m to n, plus summation bk, where k varies from m to n. So this will become the summation ak plus bk. We can add these two. K is equal, k varies from m to n. And if there is a generalized distributive law, c is any number which is outside from this summation ak, k varies from 1 to m, so this will become summation c dot ak. And if we discuss about the product of two terms ek, k varies from 1 to n, and product of bk, these are the sequences. So in the product we can write these as the product of two sequences ak dot bk. Ak is equal to k plus 1 and bk is the sequence of is equal to k minus 1 for all integers k. Write each of the following expressions as a single summation. Summation ak plus 2 into summation bk, where k varies from m to n in both these sequences. This is the first part. So we solve this first part. Here is the solution of this part. So we can write it as, by the substitution, we put the value of ak and bk, so this will become k plus 1 plus 2 into k minus 1. From here we put the value of ak and this is the value of bk. And by the previous theorem we can write these two as the product of this 2 into k plus 1, and so these two terms can be added, so we can write k plus 1 plus 2 into k minus 1, so this will become 3k minus 1. K varies from m to n. And in the second part, where the product of ak, bk, k varies from 1 to n, so k is equal to m. So now we take the product, we put the values of ak and bk, we put the values of these two sequences ak and bk by substitution. Now since these are in the product, so we can write these two terms such as k plus 1 into k minus 1. So by the algebraic simplification you can write it as the product of k square minus 1. So this is the simple solution of this example. Here the change of variable, you can say we observe that k summation k from 1 to 3, k square is equal to this will become, if we put k is equal to 1 square, plus if we put k is equal to 2, this will become k 2 square, plus if we put k is equal to 3, so this will become 3 square. And similarly for I square, I varies from 1 to 3, so this will become, if we replace the value of I 1, so this will become 1 square plus if we put I is equal to 2, this will become I 2 square plus if we put I is equal to 3, so this will become 3 square. So we observe that these two summations are equal. This equation also illustrates the fact that the symbol used to represent the index of a summation, it can be replaced by any other symbol as long as replacement is made in each location where the symbol occurs. As a consequence, the index of a summation is also called a dummy variable. A dummy variable is a symbol that derives its entire meaning from its lower to outside of the content, both before and after. So the symbol have another meaning entirely. Now we discuss the transforming a sum by a change of variable. Transform the following summation by making the specified change of variable. Summation 1 over k plus 1, k varies from 0 to 6. So change of variable j is equal to k plus 1. First we calculate the lower and upper limits of the new summation. When k is equal to 0, j is equal to k plus 1, it means it's 1. When k is equal to 0, then it means j is equal to 7. Thus the new sum goes from j varies from 1 to 7. So the next, to calculate the general term of new summation, you will need to replace each occurrence of k by an expression in j. Since j is equal to k plus 1, then k is equal to j minus 1, you can write here. So hence you can say 1 over k plus 1 is equal to 1 over, we put the value of k as j minus 1, so this is 1 over j. So we put the steps together to obtain k from 0 to 6, 1 over 1 plus k is equal to k, j varies from 1 to 7, 1 by j. So we can transform a sum by change of the variable. Upper limit appears in the expression to be summed. We transform the following summation by making the specified change of variable. Summation k combination n plus k, k varies from 1 to n. We change the variable j is equal to k minus 1. We transform the summation obtained in part A by changing all j's to k's. This is the second part of this example. Now we try to solve this. When k is equal to 1, it means the j is equal to k minus 1. So 1 minus 1, when we put k is equal to, so here k is equal to 1, then it's equal to 1 minus 1, this is 0. So the new lower limit is 0. When the lower limit is 1, then and the new limit will become 0. And when k is equal to n plus 1, then j is equal to k minus 1. We put the value in k n plus 1 minus 1, so this will become n. So the upper limit is now new upper limit is n. Since j is equal to k minus 1, then k is equal to j plus 1. And also we note that n is a constant as far as terms of the sum are concerned. It follows it. So k over n plus k is, this will become j plus 1 over n plus j plus 1. And so the general term of the new summation is we replace all the values j plus 1 over n plus j plus 1. And here we can say k over n plus k, summation k varies from 1 to n plus 1. So this can be written as, we replace the value of k, so we put the value of k as j plus 1 and substitute the limit from which was k 1 to n plus 1. This will become 0 to n, which we have already proved in the previous slide. So this will n plus k, we replace the value of k as j plus 1. Now we change all the j's to k's in the right hand side of this equation. This will give us summation j varies from 0 to n, j plus 1 over n plus j plus 1 is equal to summation k from, we replace j's with k's, so k is equal to 0 to n k plus 1 over n plus k plus 1. If we combine these two equations, we can say this equation is equation number 1. I put here this equation as 5.1.3 and this 5.1.4. So if we combine these two terms, these two equations, equation 1 and equation 2, so the result will become, we combine these two, the result will become summation k varies from 1 to n plus 1, k or n plus k, which will become summation k from 0 to n, k plus 1 or n plus k plus 1. So this is our required result. Now is the new definition, factorial definition, notations. For each positive integer, the quantity n factorial denoted by this n factorial, you can write it as the marks of an exclamation, is defined to be the product of, is denoted by the product of all the integers from 1 to n. So this will, the n factorial is equal to n, n minus 1, n minus 2, n minus 3. At the end you can see that 3, 2 and 1. 0 factorial denoted by 0 factorial is defined to be 1. 0 factorial is always equal to 1. You can calculate from it, from the calculator machine. Recursive definition for factorial is the following, given by any non-negative integer n, n factorial is equal to 1 if n is equal to 0, and if n is greater or equal to 1, then this will become n into n minus 1 factorial, and you can write n minus 1 factorial as n minus 1 n minus 2 factorial. So the process of this process will reduce to the digit 1. The next example illustrates the usefulness of recursive definition for making computations. In this example we discuss the first 10 factorials. 0 factorial, 0 factorial is equal to 1, and 1 factorial is also equal to 1. This is understood. 2 factorial is 2 dot 1, which is equal to 2, and 3 factorial is 3 dot 2 dot 1. We reduce all these numbers, so this will become 6. 4 factorial is 4, 3, 2, 1. This is 24, and 5 factorial is 5, 4, 3, 2, 1. So this will become 120. And 6 factorial is 6, 5, 4, 3, 2, 1. Similarly, this process is repeated. So the answer 1 into 2, 2 into 3, 6, 6 into 4, 24, 4 and 24 into 5. So this will product this multiply with 6. So the answer is 6, 7, 20. 7 factorial, similarly we can write we can here also write it 7 factorial as 7 dot 6 factorial. So the answer of 6 factorial 720 if multiplied by the 7, so this will give us 7 factorial. And similarly with 8 factorial, if you can also write 8 factorial as 8 into 7 factorial. If we multiply the answer of the 7 factorial with 8, this will become 8 factorial. And similarly, you can see a 9 factorial, 9, 8, 7, 6, 5, 4, 1. So this will become 3, 6, 2, 8, 8. So if we stop the product element, you can write, for example, if we want to stop about this 9 factorial at 6, so we can write 9, 8, 7 and 6 factorial. All these terms are from 6 factorial. So in this way you can reduce the factorials into small numbers, but we have to know about the basic knowledge of factorial. Now here we compute with the factorials, we simplify all the expressions, these expressions 8 factorial over 7 factorial, 5 factorial over 2 factorial and 3 factorial, and the third part 1 over 2 factorial into 1 over 2 factorial into 4 factorial plus 1 and the d part is n minus n plus 1 factorial over n factorial. In e part we have to compute n factorial over n minus 3 factorial. First 8 factorial by 7 factorial. You can write 8 factorial as 8 in dot 8 minus 1, mean to say 7 factorial over 7 factorial. So we stop here because the denominator is 7 factorial, so this will cancel to each other. So answer is 8. In the second part, 5 factorial over 2 factorial into 3 factorial. The 5 factorial may be written as 5.4.3. You can also write 3.2.1, but we stop here 3 factorial because the denominator is also 3 factorial, so we can cancel these two terms. So denominator is 2 factorial, so 5, 4, 20 over 2, 2 factorial, you can expand it 2.1, so the answer is 10. And the next example C, 1 over 2 factorial, 4 factorial plus 1 over 3 factorial, 3 factorial. So you can write 1 by 3 factorial, 4 factorial dot 3 by 3. We multiply and divide by 3 in this expression, plus, and in this expression we divide and multiply by 4. So this will become 3 3 over 3 into 2 factorial 4 factorial. This can be written as 3 dot 2 factorial and 4 factorial plus 4 over 3 factorial 4 into 3 factorial. Now you can simplify this as 3 over 3 over 3 factorial 4 factorial plus 4 over 3 factorial into 4 factorial. This 4.3 factorial can be written as 4 factorial, and this 3.2 factorial can be written as 3 factorial. So we can the denominator, both of the denominator of the expression is same, so we can take as LCM 3 factorial 4 factorial. So we add the above two terms, so 7 over 3 factorial 4 factorial, so the answer is 7 by 144. Similarly, n plus 1 factorial over n factorial, you can write n plus 1 dot n. We reduce 1 by 1. So we stop here at n because the denominator is also n factorial. Cancel out these two terms, so this will become n plus 1. And similarly for n factorial over n minus 3 factorial. We expand these n factorial up to n minus 3 because here the denominator is n minus 3 factorial. So we can write n minus 1 to n minus 3 factorial over n minus. So we cancel these two terms. The answer will n into n minus 1, n minus 2. So we can simplify this. So we get n cube minus 3n squared plus 2n. Special factor cases. Let n and r be the integers with r is between 0 to n. The symbol n combination r is read as n choose r and represents the number of subsets of size r that can be chosen from a set with n elements. The formula for computing NCR, you can also write it as, you can also read it as n combination r. For all integers n and r with r between 0 to n, NCR may be written as n factorial or r factorial into n minus r. The difference of both these. Here we compute NCR by hand. So using the formula for V2R to evaluate NCR through the following expressions. 8C5. 8C5 is may be written as, so 8C5 may be written as 8 factorial or 5 factorial 8 minus 5 factorial. So we simplify these two terms. 8 factorial may be written as 8 factorial up to, we can here write up to 5 factorial and then cancel out with this 5 factorial, and this 8 minus 5 factorial is 3 factorial. So we can simplify this as we discussed in the previous slide. This will become 56, and 4 combination 4C4, this will also become 4 over 4 factorial into 4 minus 4 factorial. So the answer will be 4 factorial over 4 factorial into 0. So this 4 factorial can be written as 4321. So 4321 into 0 factorial is 1. So the answer is 1. And similarly, you can say n plus 1 c1n. So n plus 1 factorial over n factorial into n plus 1 minus n factorial. After the simplification, we will get the answer n plus 1. If we discuss here about the lecture summary which we discussed in this lecture, we have discussed about the sequences, where is the set of all, the domain of sequences is a set of all positive integers. Alternating sequences, we also discussed about the alternating sequences. We have discussed about the summation notation. This was a summation notation where we take k from 0 to 1 or k from m to n, and product notation. This gamma type is used for the product notation. And also we discussed discuss about the here we discussed about the properties of the sequences, change of the variable we also discussed, and factorial notations is also discussed in the previous in this lecture.